I wanted to talk to you a little bit about what Newton's third law is. Newton's third law refers to the force between two objects, and we're going to look at two objects in an isolated system. So an example would be, say, me pushing on the table. Well, I push on the table with a certain force, but the table pushes up on my hands with an equal magnitude force and opposite direction force. It pushes up on my hands. And that can be a little unintuitive. For example, if you imagine a car smashing into a mosquito, if you're the mosquito, okay, this huge force from the car is smashing you. That feels like a huge force. But then what Newton's third law says is that the mosquito pushes with a same magnitude force back in the opposite direction on the windshield of the car. So what we're going to do here is just prove Newton's third law from things that you know. So Newton's third law, here we're going to start by looking at a system of two objects. So the system is two objects here. And so we want to know what, if anything, can we say about the total momentum of the system? Well, it's isolated, and so we know what that means. That means that the change in the total momentum is equal to 0. And what that implies, you could also write this as change in the total momentum over some period of time is also going to be equal to 0. So what we're going to get to eventually is this claim about what Newton's third law is. So you'll see where it's going in a minute. So okay, what we can do is we can write the total momentum. So now let's write this in terms of the momentum of both of these objects. So we have delta, and then the total momentum is the momentum of object 1 plus the momentum of object 2 divided, again, by the total time is equal to 0. And then let's keep going and just write delta of P1 over delta T. I'm just distributing the T for both of the P's here. P2, delta P2 over delta T equals 0. Okay, so this is basically saying that the change in the momentum of one object over some period of time is equal to the change in the other object over that same period of time. So for example, if you've ever shot a gun, the bullet its momentum starts growing in one direction, but then the gun has some momentum, and in the other direction, it's the same change in momentum. So, okay, now to eventually get to Newton's third law, what we have to do is change what we're considering as the system. So if instead we consider the system as just one object, then what is the change in the momentum if say this other ball 2, which isn't in the system of 1, if it acts on it? So what can we say about the momentum? Well, we can say that basically the change in momentum of this object 1 isn't going to be 0. One thing that you might have read before or in the pre-reading, which you should look at before this, is that the average force on some object is equal to the change in its momentum over the change in time. So we can write this as the force of object 2 on object 1. So what this just means is the force of object 2 on 1. And so the change in momentum of 1 is, over some period of time, is going to give you the average force of 2 on 1. So now we can do the same thing, but look at the second object as the system and ask, what do we know about the momentum? Well, we know that the momentum of 2, the change of that momentum over that same period of time, is going to be equal to the force of 1 on 2. So this is object 1 on 2. So basically these are just saying there's only one object that's interacting with 1 here and 2 here, and that's the other object. 2's acting on 1, 1's acting on 2. And so the force, the thing that changes the momentum, is the other object. And that's all that these statements are saying. Now that seems a little bit obvious, maybe a tautology, but if you put this together with this up here, put these three equations together, I'm going to call this A, B, and C. So when you look back at this, you'll know what this is referring to. But A, B, and C together are going to give you that, okay, so let's plug in force of 2 on 1 for the change in momentum of 1 over that time. So average force of 2 on 1 plus, and then I'm going to plug in up here, this is a vector, I can't forget that, the force of 1 on 2, that's just the change in the momentum of 2 over that time period, is equal to 0. So this is true for the averages, the average of the force, but it's also true, we have to do a little bit of calculus, which you don't need to know for this class, but this is also true just for the forces in general. So we can just write the force of 2 on 1 plus the force of 1 on 2 is equal to 0, or what that implies is that the force of 2 on 1 is equal to the minus force of 1 on 2. So this is Newton's third law. And that's basically what I stated at the beginning, where 2 is maybe the mosquito and 1 is the car. And you can see the force on 1 has to be equal and opposite to the force on the other if it's in a system like this where just 1 is acting on the other.